slide, I put some very naive example of the corrections, the next to leading order corrections to the decay of a virtual photon into a pair of quark-antiquark. Essentially, we have some correction which involve a closed loop or a quantum fluctuation of the vacuum, which has to be combined with contributions involving additional particles in the final state. And the problem is that these objects contain some singularities. And we need to cancel these singularities in order to get a number. So we need to add, usually, some counterterms that fix the problems in these two pieces, the loop and the real correction. The point is that when we use dimensional regularization, these singularities manifest as poles in epsilon. And the point is that only when we put all these ingredients together, the poles are going to cancel. And in the traditional approach, this cancellation takes place after integration, after integrating the loop integrals, after integrating the phase space, and of course, after adding the counterterms. So, what is the loop tree duality? Let's start to center into this technique. We know that the loop amplitudes are a bottleneck. They're very complicated. We cannot compute them in a straightforward way when we start to go to higher orders, because they have singularities, they have thresholds. So even if we want to do something numerical, it is not straightforward. On the other hand, we know that there are theorems, very general theorems, that guarantee that these singularities will cancel when we consider physical observables. If we are computing something that is going to be compared with experiment, these singularities must cancel. And finally, this real radiation that we were talking in the previous slide is defined in an Euclidean space, because there are phase space integrals involved. So why don't we rewrite the loop amplitudes in such a way that they look like the real radiation? Because if we do that, we can put everything together and cancel all the singularities. And this is exactly what the loop tree duality allows us to do. We start with loop amplitudes, which are defined with a virtual internal momenta, that is a particle that is off-shell, and that are defined in the Minkowskian spacetime. When we apply this formalism, the loop tree duality, we end up with on-shell cut momenta, that is, we cut the diagram, like in this picture, and we put that line on-shell. So this particle represents an on-shell state. And by doing that, we remove one degree of freedom of the integration, and we have something that is defined in an Euclidean spacetime, or an Euclidean space, if we want to say. So by using this loop tree duality, this idea, all the ingredients appearing in this framework start to look very similar. And in this sketch, I wanted to more or less explain how the LTD was developed and how it was evolving through the time. So in 2008 and 2010, we started to see that virtual amplitudes can be rewritten as tree-level-like objects and defined in an Euclidean space, as we were saying before. But then we go beyond that, and we started to study how this new representation allows us to localize the infrared and threshold singularities. This was done in 2014. By using some mappings and putting into the game the real amplitudes, we achieve a combination of we achieve a combination that was finite, that was integrable, something that was integrable, and that represents the cross-section in a purely four-dimensional way. Of course, the UV counterterms that we were mentioning before were converted into dual amplitudes by using a set of formulas that were developed in 2013. So by using this formalism inspired into the loop tree, in the loop tree duality, we managed to obtain a local four-dimensional representation of cross-sections. And this is something very important. Local means that we cancel the singularities before performing the integration, not after, before. So we can drop the epsilon and write everything in 4 dimensions. This is extremely important because allow us to perform numerical integrations without having to take care of these singularities, this regularization. Everything is going to cancel while we are doing the numerical integration. So, oops. Okay, and last year, 2020, and also during this year, we managed to obtain a new representation of the loop tree duality in which we generalize previous result and we obtain new properties. In particular, during 2020, we published these 4 papers. This year, we also keep on publishing more developments, but I would say that last year was like the beginning of this revolution. And the idea was using the strategy of the nested residues. So the starting point, we have multi-loop Feynman integrals or scattering amplitudes. Essentially, for the formalism, it is the same. And we iterate the application of the Cauchy residue theorem to remove 1 degree of freedom for each loop momentum. In our studies, we have been removing the energy component, but the formalism can be extended or can be modified, let's say, to cancel other degrees of freedom. And the idea, or something that is very important, is how to set up the notation. So what we have done in our first studies was to classify all the momenta of the propagators that share the same dependence on the loop momenta. Loop momenta means integration momenta. This L that appears here in this integral, these are the loop momenta. So we classify all the momenta flowing at through the different propagators according to their dependence on these integration variables. And this is what defines a set of momenta, what we call a set of momenta. On the other hand, we have to write the Feynman propagators in this way, where essentially we separate the energy component, this IS0, from the on-shell energy of the associated particle, this Q+. Essentially, the Q+ is the solution of the on-shell equation and includes the dependence on the Feynman prescription. So using this notation, we use any L loop and particle scattering amplitude in this way. So the next step is to define this iteration in a compact way. So we have here a formula where essentially we define the residue of the dual. The dual is recursively defined by this equation. And then here, in this part where we put the imaginary part of this vector eta times q, we are selecting essentially which component we are removing from the integration from the loop momenta. If we select this eta to be the vector 1, 0, then this prescription is equivalent to remove the energy component. And the point is that here we are extending function to the complex plane. We are extending, we are promoting this energy here to the complex plane, and we have to select only those poles that are in one part of the complex plane. And for our convention, we will work with this prescription. We choose the negative imaginary part, those poles that contains that fulfills this condition here. The point is that this dual representation for an amplitude with L loops implies that we have to evaluate L iterated residues. So this agrees with the previous concept that says that the number of cuts that we have to do within the loop tree duality formalism is equal to the number of loops. In this way, we open the amplitude into something that looks like a tree-level amplitude. And then we have to sum over all the poles. And this is something important, and this is essentially what we discovered during last year, that when we sum everything, there are several contributions that vanish. And the point is that these contributions that cancel between each other and are not present in the final result contains spurious singularities. They are what we call displaced poles, and these contributions would introduce some instabilities, some singularities that are not physical, so they cannot be in the final result. The other discovery that we have done last year is that thanks to this cancellation of displaced poles, the formulas that we are getting for the dual representation are very compact. For instance, we consider this, that is the so-called maximal loop topology, that essentially contains two vertices, here, here, and L+1 lines or set of lines. This means, by using the notation introduced here of the idea of sets of momenta, each line here can have attached an arbitrary number of external particles, and this decomposition will be valid. And the point is that it is something very compact, and we can see that we only need to add L dual contributions with a very clear definition of which lines are set on shell, which lines are set on shell but with reverse momenta, and which lines are left off shell. And the important thing of this topology, the maximal loop topology, is that it can be considered as a building block to describe something that is more complicated, and that any one and two loop amplitude can be described by these MLT topologies. Regarding this, we have provided some recursive, inductive, proof of this formula in this paper from 2021. We keep on studying these factorization properties, in the dual representation, and effectively we confirm that the MLT, that is this object in the right-hand side of the convolution, is a factor that always appears when writing objects or amplitudes that are much more complex than the MLT. For instance, the next to maximal loop topology that has three vertices and L+2 lines can be described as the sum of these two convolutions, where essentially we are putting on shell some specific sets of lines. The same can be done for something much more complicated, that is the next to maximal loop topology, we also have these factorization formulas. And even more interesting, we have been dealing with the so-called next to next to next to next 4n maximal loop topologies that are these very complicated diagrams. And we also managed to prove that this dual representation is extremely powerful to show us factorization formulas. And why are these factorization formulas important? Because they allow us to describe the singular and causal, I will explain a bit more about this causal structure of any amplitude in terms of something that is simpler. In this case, we are reducing a multi-loop problem to something that has this multi-loop complexity hidden into the MLT component. And then we have some object that is in some sense universal, but that can be computed once, and then we can extend it for any number of loops. Regarding this concept of causality, well, this is something extremely important and something that we discover when we use the dual representation and we add everything together. In first place, the cancellation of the displaced poles implies that some contributions vanish. So naturally, the dual description was compact in the sense that several cancellations take place. But when we put everything together, when we force some additional cancellation transformations, we realize that more terms cancel. And essentially, all the only contributions that remain in the final result are characterized by an aligned flux of the internal momenta, of the momenta that we are cutting. Essentially, if we go to this to this decomposition, here we have a lot of terms where we are leaving one particle off shell. The point is that when we sum all these terms, we can think that this line I has a superposition of fluxes. It has the superposition of a momenta flowing from right to left and the other one from left to right. But when we sum everything, the contributions that are not aligned cancel. So in the end, we can interpret this MLT diagram in this very, very, very simple way, in which we introduce the concept of causal propagator that is equivalent to indicate which lines are set on shell and how the flux, the momenta flux is going through it. So we tested this idea with more complicated examples just to be sure if it was not let's say a particular case for the MLT. And it turns out that it was something more general, that if we take something like this thing, that is an MLT, we also have a structure involving products. Now it involves products of these lambdas, the things that we call the causal propagators. And even more, if we go beyond, if we go to a Mercedes-Benz diagram like this one, that is what we call the next to maximal, then we also have products of these lambdas. So in the end, it turns out that this lambda seems to be the building block of this representation. So this is something that this causal representation, this representation in which we only use these lambdas to write the amplitude, are something is something very general that has very important advantages, because since we have same sign combinations of on-shell energies, so look here, for instance, in these definitions, we also have sums of these Qi0 pluses. So since these Qi0 pluses are positive quantities, if we forget about the complex part, they are positive, the real part is positive. So we don't have a sign changes in the denominators, which make it more stable numerically. Instead of having zeros that appear when we are evaluating numerically these integrals, these unphysical zeros will be never present. And only the physical thresholds, the physical singularities, will remain. And just to see an example of the importance of dealing with this causal representation, here we see in this in the left side, in the left plot, we see the dual representation without the causal representation, I mean without using the lambdas, or if we use directly the lambdas. If we keep in the description terms that contains non-aligned contributions, that is, instead of having these lambdas, we could have something involving Qi0 minus Q20, is something that could eventually vanish at integrand level. If we only work with the causal representation, our result is much more stable. And here in the plot in the right, this nice plot, we see these white lines. These white lines are essentially the graphical representation of these instabilities that appears in the plot that I previously explained. So what we have been doing in this paper by Aguilera Verdugo et al. In 2020, that is published in JHEP, we study the numerical implementation of this causal representation and compare the results with those provided by known numerical codes, such as Fiesta, for instance. And we use some benchmark topologies, which were the next to maximal loop topology and next to maximal loop topologies with 3 and 4 loops. And we did a scan varying the values of the masses. Here we use something very important because, as you know, these objects usually have ultraviolet singularities. So in order to avoid that, we raise the powers of some of the lines in such a way that we have a suppression and we don't have these UV singularities. So we use this formula where essentially we derivate the causal representation of an next to maximal or next to maximal loop topology with respect to the Qi zeros, and we get the causal representation of this amplitude involving higher powers of the propagators. And as you can see from this plot, the dots here, the black dots, are essentially the numerical values that we get with the Fiesta, that is, let's say, a standard framework for doing this kind of calculations. And the solid lines corresponds to the values, the numerical values that we get by using the causal representation obtained with the loop tree duality. And we see a perfect agreement. So, since it was very promising to be able to write the amplitudes by using only these lambdas, we keep on investigating on this with several topologies and several processes that were presented in these papers here. In particular, in the last one, in European Physical Journal, one of our collaborators published a code, Lotti, which is able to obtain a causal representation of generic multi-loop, multi-lex amplitudes. And on the other hand, we also were able to develop a graphical or a geometrical interpretation in terms of entangled thresholds. These causal propagators that we introduced before corresponds to a threshold of the diagram. That is, a singularity that split the diagram in two parts. Each diagram, when we go to higher orders, contains several thresholds. So the causal representation involves combining, like entangling these thresholds in such a way that they are compatible. So we have to know which are the compatibility rules. Moreover, we can conjecture that any multi-loop, multi-leg amplitude can be written in this way. That is, the causal or a causal representation of the amplitude. And what we ask is it possible to obtain this representation without computing the residues? And of course, the answer is yes. And at least there are two ways. One is the analytic reconstruction that is implemented in the code Lottie that I mentioned before. And the other one is a geometrical reconstruction. So in order to develop the geometrical reconstruction, that is one of the topics of this talk, we have to define some previous concepts. Diagrams are made of vertices and the so-called multi-edges that are bunches of propagators which connect two vertices. In this plot, in this graph here, we have these two vertices that are connected with several lines which can be collapsed into a single line. This single line is a multi-edge. Multi-edge define a basis of momenta that allow us to define something that we call the vertex matrix, and this contains all the information about the causal structure of a diagram. And the other concept that we need is the binary partitions. Binary partitions are subsets of the vertices that split the diagrams into two connected things. So essentially here, there are in red a partition involving this vertex and this vertex that is clearly disconnected. If we consider only this set, these 2 points are not connected. On the other hand, these 2 green points are trivially connected. There is a line going from one to the other, but also the remaining 2 are connected. So the picture in the right represents a connected partition. The point is that by relying only on geometry, we can calculate or generate all the causal propagators or the all the lambdas that we found by doing an explicit calculation based on the loop-tree duality. And there are some rules that allow us to identify them. Essentially, we have to compute all the binary connected partitions of the diagram. And this is enough to generate all the lambdas. On the other hand, we have some idea of the complexity or the order of the diagram that is related with the number of vertices. This tells us how many thresholds we have to entangle to obtain the causal representation. How, let's say, in each term, how many lambdas are multiplied. And then we have to define how to which of these entangled thresholds are going to be present in a causal representation. So we have some rules, like multi-edge are cut at least once. So all the contributions involve cutting all the multi-edges at least one. The causal propagators are associated to disjoint partitions of the diagrams. This means that if we follow these lines that appear here, for instance, we disentangle the diagram in such a way that it is that it can be done smoothly without breaking any partition. This situation of let's say not fulfilling the condition B is shown in this diagram, where we see that the lines representing the thresholds, the causal thresholds, intersect. So we cannot split the diagram into two connected subdiagrams. And also, the fluxes of the lines that are being cut must be aligned consistently. And this is a very important condition that led us to the definition of causal fluxes. So, an example of how this algorithm for doing the geometric reconstruction works, we consider here an hexagon, one loop diagram with 6 vertices, and we put one external leg per vertex. So with this information, we have the equations, the conservation equations for each vertex. Then we will the vertex matrix. With this vertex matrix, we can identify which are the connected binary partitions and generate the causal propagators. And then we have to use these selection rules that we mentioned before to detect which are the possible entangled thresholds. And then we obtain a causal representation. That here it looks a bit small, but here we have it bigger. And essentially, we have products of these lambdas. Since the hexagon has 6 vertices, by using the formula that we previously mentioned, it has complexity 5, order 5. So it involves products of 5 lambdas. So at this point, we are modifying a bit this the loop tree duality and thinking in a bit different way how to get the cross section. So the point is that by studying the virtual amplitudes, we managed to obtain a universal description of infrared and threshold singularities by using causal propagators. And this was first introduced by using a slightly different notation in this paper in 2019. And then in 2020 and 2021, we deepen into the consequences of the causal representation, exploring how to generate this causal representation by using geometric and algebraic algorithms. With this, we expect that in the future, we can combine real amplitudes by using mappings and obtain the causal representation of properly defined ultraviolet and initial state radiation counterterms to get not only a local 4-dimensional representation of a cross-section, but also a causal one. I mean, something that combines all the simplifications which are introduced by forcing causality with all the advantages that we have by having local cancellations of singularities. So we expect that this framework could produce an algorithm to compute cross-section much more efficiently. But at a certain point, when dealing with the causal configurations and some intermediate steps, we have to think about optimization or probably alternative algorithms to speed up the calculation. And at this point is where we started to explore how to put into the game quantum algorithms, something completely new applied to this kind of problems in particle physics. And in May, we published a paper in which we were able to recognize or to identify the causal fluxes that is a crucial ingredient to obtain the causal representation by using the Grover's algorithm. This algorithm essentially puts one qubit, that is a quantum bit, to represent the orientation of each edge or multi-edge. And then we impose some logical conditions to select configurations that don't have cycles. By doing some theoretical studies, we realized that the causal flux is equivalent to configurations without cycles. So we force this algorithm to look into those configurations that are non-cyclical. And here we define an initial state that was the superposition of all the possible orientations of the lines of a diagram, of the edges of the diagram. If you think about this number, it grows exponentially with the number of internal edges, like 2 to the n, because we have two possible orientations. So there are several states, a huge number of states that can be that must be tested to determine whether they are causal or not, if they lead to configurations that are cyclic or not. So we profit from this algorithm because essentially the Grover's algorithm can allow us to evaluate all the possible states at the same time. And from there, maximize the probability of measuring those that satisfy some condition, that are the so-called winning state. So we force this algorithm to associate the winning states to those that are non-cyclic configurations. And we define some operators that are part of this algorithm, and we implemented this algorithm by using Qiskit and in a simulator by IBM, and we studied several topologies. We have to use some technicalities to enhance the performance of this searching algorithm because of some technical details. And the point is that we managed to identify the configurations that are causal by using this algorithm. Here you can see an example for this triangle that essentially it is a one loop diagram in which we have 3 vertices. And here we see the quantum algorithm, the quantum code as shown by Qiskit, by this platform for implementing this kind of computations. And and more recently, we have been working in some optimizations of our previous codes, which tries to reduce the number of qubits that we need to do this implementation. And this is possible thanks to some very interesting properties of the adjacency matrix, something that is connected to the vertex matrix. And with these new implementations, we managed to reduce the number of qubits. We managed to implement it in the existing simulators because they are limited by the number of qubits. And we managed to successfully identify the causal fluxes. So with this, I arrived to the conclusions. And I would like to say that the loop-theory duality is something very important to cleverly rewrite the Feynman integrals, going from Minkowski to Euclidean space, that we can achieve a local cancellation of infrared and ultraviolet singularities when we are dealing with physical observables, and that the new representation of the loop-theory duality leads to expressions that are manifestly causal and that avoid several unphysical singularities. And this very compact formula that we are obtaining have a very strong physical and conceptual motivation. Also, that by using geometrical rules, we managed to reconstruct a causal representation for multi-loop amplitudes, and moreover, that we speed up this reconstruction by identifying the possible causal fluxes through quantum algorithms. That this is something that can have very important consequences and can help us to break up the precision frontiers in theoretical physics. So with this, I would like to thank you for the attention. If you have any questions.
Thank you, Herman, for your very nice and interesting talk. So if anyone has questions, you can raise your hand or just speak. Don't be shy.
Hi.
Yes.
This is Benito.
Go ahead, Benito, please.
Can I ask a question?
Yes.
Okay. So thanks for the very interesting talk. So I was a bit puzzled by the use of causal in your method.
Yes.
Is this I mean, first of all, because you are going to Euclidean space, and it's not, I mean, to me, it's not so clear in what sense you can understand what is causality in the Euclidean section. So, I mean, if you could point me out into, I mean, in what sense you're saying that this is causal, and also if this is related in some sense to the standard. I mean, what we study as causal perturbation theory in quantum field theory is the Epstein-Glaser perturbation theory. If this is somehow related or building up on those ideas, so I guess that would be the question.
Okay. Well, first regarding the Minkowski versus Euclidean and causality. Well, causality is defined. I mean, by using the light cones, the idea of events that are laying inside with or outside the light cone of something. I agree that this is something that is defined by using Minkowski geometry, I would say. But the point is that this representation, this causality that we are introducing is done at the level of the diagram. So here you are ordering the flux of information inside the diagram from one partition to the other. And this is independent of being Euclidean or Minkowskian in the sense that we are not integrating at this point. What we find is that the information associated to the causal thresholds can be encoded into these lambdas that are here. And by the because of how we are implementing this computation, it turns out that it only involves information that is associated to the Euclidean part of the integration. I mean, it is not that we are defining at this point the concept of causality in an Euclidean space. It is just that we are defining the integration in an Euclidean space, and we associate the concept of causality with or causal thresholds with these objects lambda that only depend on variables defined in an Euclidean space. Of course, there is a connection because we are putting the on-shell conditions. So by doing that, it's like the energy component is being fully determined by the spatial part. So that's where this connection enters.
Okay.
Yes.
Okay, thank you.
Yes.
Yeah. No, you were going to say something about causal perturbation theory, maybe.
Yes, I was about to say that. This is a question that we are having a lot of times. I mean, it turns out that the time order perturbation theory, let's say the classical way of doing that, involves considering all the possible cuts. So you take the let's say something like this. You start to take the diagram and compute all the possible entangled thresholds, all the possible ways of taking the diagram and decomposing it into substructures with a consistent flux. The point is that some of these configurations are degenerative in the sense that when we impose momentum conservation in the external legs, some of these configurations are equivalent. And the loop tree duality managed to select a subset of these configurations that is non-degenerative. So this is something that, for instance, has been discussed in a paper by William Torres, where essentially he developed some formulas, all loop formulas, to obtain this causal representation for the loop tree duality. And not all the configurations that are associated or that are present in the classical time order perturbation theory appears there. But if we look into those terms that are different, it turns out that they are related by global momentum conservation. So essentially, I would say that the loop tree duality and time order perturbation theory are related by that, by some conditions associated to momentum configuration, to momentum conservation, sorry.
Mm-hmm. Okay, thank you.
You're welcome.
Thank you very much for the question. So I think that we have to move on, and we have to thank you, Germán. Thank you, Germán, for the talk. Now we have Benito Juárez Aubry. Can you share your screen?
Hi. Yeah, I just continue talking because I just asked the question. So it's a smooth transition, you say?
Yes.
That's the whole point.
Yeah. Can you put it in full screen mode?
I can put it in full screen mode, or presentation even better.
Okay. So now we have our next speaker. He's Benito Juárez Aubry. He's has been related with his job is about general relativity, also in configurations like Casimir effects in quantum field theory. And here the topic that he is going to talk about is related with that. Thank you, Benito. Go ahead, please.
Okay, thank you. Thank you very much for the kind invitation. I'm very happy to join you and to be here and to share my relatively recent work on the Casimir effect. So I'm going to talk about a couple of papers that I wrote with Ricardo Weder, who is at the Institute of Applied Maths here at UNAM. And the project that we were working on last year and the year before, I believe, is about the Casimir effect. So this is a very, very important effect in quantum field theory. And if you're familiar with it, you will know why it is relevant. But if not, I'm going to tell you very quickly why it's interesting. So the Casimir effect says that the ground state of let's say a free field, but it could also be for some more complicated system. The ground state for a free field inside a box has non-vanishing energy. So if you think of the ground state in Minkowski spacetime, so where there are no walls from a box, then the ground state energy is zero. That's the energy of the Minkowski vacuum state. No particles, zero energy. The moment you put the field in a box, the boundary conditions play a significant role, and you find that the state of minimum energy actually has non-vanishing energy. And this is quite important from several perspectives. I mean, one of them is that it almost speaks to you of the reality of the vacuum state in physics, because you can actually measure its energy. And so for a long time, people have been trying to measure this effect, and it comes essentially in two guises. One is, say, the static Casimir effect, where you have a fixed box, and another one is when you have a dynamical Casimir effect. That's when the box walls are moving, for example. And experimentally, it's very challenging to measure it. In fact, until very recently, there were no claims to have measured the dynamical Casimir effect. But well, very recently, there is some claims. And our work here has to do with studying the Casimir effect with a particularly interesting set of boundary conditions. And these are called dynamical boundary conditions. They're not called dynamical in the sense that the walls of the system are moving, but they're called dynamical in the sense that the boundary condition that you impose on the system depends on time derivatives of the field at the boundary. So in this sense, it's as if though you had dynamics both in the bulk of the system, but also you had some boundary dynamics and boundary observables associated to this problem. And this is interesting for physical, mathematical, and experimental reasons, as I will explain. So let me now just jump into the question. Please feel free to interrupt me at any point if there's an important question, or even if it's not so important. But if you feel that you're getting the urge to ask, please do so. And then I will adapt my time to rush in a bit towards the end if needed. But I prefer if the questions are asked as we go. Okay, so after brief motivation, I'll describe the classical problem that we're interested in and the quantization of this system afterwards. Then I will go directly into the study of the Casimir effect, which involves some renormalization stories and trying to define energies in an appropriate way. And then I will conclude with some final remarks. Okay, so for the motivation, these dynamical boundary condition systems are very interesting for several reasons. So one of them has to do with the idea of boundary degrees of freedom. So this is a question that I think is appearing more and more in physics. So for example, with isolated horizons, when people try to study black holes and associate entropy to the horizon viewed as a surface in space-time, then people are thinking if this entropy is associated with microscopic degrees of freedom, then these are certainly boundary degrees of freedom, and we would like to understand how to characterize them rigorously. So there you would expect some kind of boundary, if you will, dynamics in order to have boundary degrees of freedom. Of course, in string theory, brains, holography, ADS-CFT, and all these interesting subjects, one is very interested in the idea of boundary degrees of freedom because, well, as some of you know, in the ADS-CFT conjecture, you try to understand what is happening in, let's say, quantum gravity in anti-de Sitter spacetime by studying dual field theories in the boundary of anti-de Sitter. Also very close to these ideas is holographic renormalization, which actually in this context also boundary conditions with derivatives appear, let's say, in the high energy physics context. Other theories that are more standards like Maxwell-Chern-Simons and so on could also be interesting from this point of view. And also in condensed matter and topological insulators, we're also interested in this notion of boundary degrees of freedom. In particle detectors, if one can think of detectors, point-like detectors as defining boundaries to a system. So for example, with a string with masses attached at the end, and you would like to see whether the masses on the extrema can detect how the string is excited, and in a sense, if these masses on the extrema could work as particle detectors. Here, not so much in the sense of, let's say, a CERN or a big particle detector, but in the conceptual sense, like Unruh de Witt detectors or the detectors studied by Unruh and Wald in curved spacetimes. And from the mathematical point of view, these kind of systems where you have these boundary conditions that are dynamical, that contain derivatives, these have been studied in the theory of differential equations since the 70s. So mathematicians have been interested in studying these systems for the reasons that they are interested in studying the systems in general, which is curiosity, but also it seems that they have interesting applications in engineering and well, in applied mathematics, this is a big topic. And going to the experimental motivation, so the kind of boundary conditions that I will study in this paper have also, they're very closely related to the boundary conditions that appear in superconducting circuit experiments. So for those of you that have some engineering knowledge or close to experimentalists, you might understand the details of this a bit better than me. But it seems that these superconducting circuit experiments are interesting actually for the experimental verifications of the Casimir effect, which makes these boundary conditions in this context even more interesting. So let's jump into the classical problem after that motivation. So I'm going to consider a scalar field defined on an interval of length L. Here L is a positive real number, and this is a real scalar. So equation 1 defines the dynamics of the system. So on the first line, we have simply the Klein-Gordon equation with a potential and a mass term. And on the second line, we have a boundary condition on the left end of the interval. So at z equals 0, we have a Robin boundary condition. So this is just the standard boundary condition that is a linear combination between the value of the field and its normal derivative at the boundary. The more interesting boundary condition is at endpoint L, where we have this dynamical boundary condition that I was talking about. So notice on the left-hand side, we have a beta 1 prime and then a time derivative, second order time derivative. So this looks a bit, again, like, well, I mean, if in more dimensions, this would look like a wave equation, but here it looks like an oscillator kind of equation. And the minus beta 1 term looks like a mass term. Now, on the right-hand side, at the boundary condition, you have sources, and sources by the normal derivative of the field at the boundary, and then the second time derivative of the normal derivative of the field at the boundary. So these are sources. And you will see that I have colored this in a particular way. So the red coloring indicates that this is like a bulk field, okay? So this is a field that lives in the bulk. And here for the blue one, I want to consider that this is kind of a boundary observable, okay? So this is only depending on T, but we can view it as a boundary observable in its own right, and then look at this system as an enlarged bulk boundary system, and this is how we shall do it. Okay, so these coefficients beta, I'm gonna ask of them some technical condition, that is that if I form the determinant of this matrix, I want it to be positive, and this is just a technical condition for the problem, okay? So now, let me try to solve the classical problem. If we are looking for time periodic solutions, then of course system 3, equation 1 becomes this equation 3, which is an eigenvalue problem essentially. But what's interesting about this eigenvalue problem is that the eigenvalue appears as well in the boundary. So these are called boundary eigenvalue problems in the mathematical literature. And it is well known for mathematicians that the natural Hilbert space of the theory is not L2 as it usually is in this kind of problems for the Klein-Gordon equation or the wave equation, but it is an enlarged Hilbert space, which is L2 direct sum C, where the complex numbers are C here, which takes into account the datum at the boundary. So this it takes into account this this boundary observable, okay? And there's a natural inner product in this space, which is a modification of your L2 inner product. So if you take two elements of this Hilbert space, which are represented like these kind of vectors, so where phi1 lives in L2 and phi2 lives in the complex numbers, and similarly for chi, then in this case, your inner product is going to look like the L2 inner product for the bulk component, and then you have to add this extra piece with the boundary component. And remember, since rho, we have asked it to be positive, this is really an honest-to-God inner product. So it cannot be 0 and it cannot be negative, so this expression 4 is correct. Okay, so from the classical point of view, we can solve this by casting the problem in the form of an abstract wave equation. And once we have done that, we know how to solve a wave equation, and we are very happy. So we introduce an operator A, which is self-adjoint. So I'm gonna say a little bit about the domain of this operator, so why it is the correct operator to introduce. So, and the way that you define it is the following: you take an element, you take a Hilbert space element in the domain of the operator, and this is how it acts. It acts with this kind of elliptic operator on the first component, and on the second component, it takes the first component and sends it to the boundary and acts with a linear combination of the bulk field and its normal derivative at the boundary. So this is what it does. So you can see that it kind of erases the information of phi2 of the boundary component of the object on which it acts. And then for its domain, there are some regularity conditions that are a bit technical. But what is more interesting to note is that, of course, as in many other boundary value problems, the domain of this operator implements the boundary condition. So you want that the boundary condition on the left endpoint holds. So this is the Robin boundary condition at z equals 0. And on the right endpoint, you impose your dynamical boundary condition. So you see, when phi2 has this form, you can exactly cast the original problem as an abstract wave equation, as in equation 7b, or as an eigenvalue equation, as in equation 7a. Just also, we know from general mathematical results that the spectrum of this operator is discrete and non-degenerate. Okay? And it's of course real because it's self-adjoint. Okay, so once we have casted the original complicated looking equation as an abstract wave equation, we know how to solve wave equations, because this is what we do as physicists basically most of our time. So given some initial data, so let's say I give you some initial data for the field and its first time derivative, because this is a second order problem. Then the solutions, I can obtain them by the functional calculus of self-adjoint operators. So this is just a standard. So in the abstract way, it looks like the first line here of equation 9, but more explicitly, I can write it as an eigenfunction expansion. So if this psi n's are the eigenfunctions of my operator A, then I can write the solution as an eigenfunction expansion. And notice that these eigenfunctions have two components. So they have a bulk and a boundary component. So this likewise has two components, the solution. Okay. So of course, this is a strong solution if these initial data are in the correct domains. Well, let's say that sufficiently regular, and they are weak if you ask less regularity. But well, this is just mathematics. And you would like so for doing quantum field theory, you would like this operator actually to be positive. And so we can ensure that with a proposition, which appears in the first paper that I mentioned, on which this talk is based. So suppose that the determinant is positive, as it is by assumption, and suppose that this potential term is non-negative, okay, for every like in the domain of interest. Then that beta 2 prime is non-vanishing, and some conditions on the parameter of your Robin boundary condition. Then you assume if beta 2 prime is positive, then beta 1 is non-negative, beta 2 is negative, and beta 1 prime is negative. And if beta 2 prime is negative, then you have the converse. Then under these conditions, all the eigenvalues of A are positive, and we can denote the smallest eigenvalue by omega 1 squared, and you have this strict positivity condition. So this proposition is sufficient, but it's actually not necessary, but it's useful to work in the context of this proposition. So just once these conditions are fulfilled, so you see this proposition is a condition on the coefficients of the problem. Okay, so if I impose those conditions on the coefficients of the problem, then we can carry out canonical quantization, okay? So we can do it in the standard way. We have a one particle Hilbert space, which is little L2, which are the complex valued squared summable sequences, and with the standard scalar product. And the Fock space of the theory is just built in the standard way out of that one particle Hilbert space, okay? So just symmetrizing tensor products of little L2 and with a direct sum, okay? The vacuum state is, of course, this vector in Hilbert space, in Fock space. And you can write down the quantum fields quite explicitly in terms of these eigenfunctions with annihilation and creation operators that are just going to satisfy the canonical commutation relations. And here the eigenfunctions that appear here, as I mentioned, have two components, and they generally will have this form. So because they are in the domain of the operator A. Okay, so let us begin by studying the Casimir effect in the ground state. So that means at 0 temperature. Then we're going to do it at finite temperatures and then for coherent states. So the way in which I'm going to do this, so there are many ways to study the Casimir effect. So because we have to compute an energy, we have to renormalize, and I'm going to do a point splitting renormalization. So point splitting regularization and then Hadamard subtraction. So this is the way in which K, for example, has introduced a renormalization in the context of the Casimir effect. So I compute the Weidmann function of the field, and this is just taking the standard form, where remember that these eigenfunctions have two components, one for the bulk and one for the boundary. And this allows me to define bulk and boundary Casimir energies, actually. So this two-point function has a bulk component, a boundary component, and a bulk boundary component. So if you use the bulk component, it's very natural to define a bulk Casimir energy, and with the boundary component, you can define a boundary Casimir energy. Okay, so I just write it down here. So for the bulk Casimir energy, I'm going to use this kind of bulk component of the two-point function, and likewise for the boundary one. Okay. So we have to subtract the singularities of the two-point function because this is what we need to do to renormalize. So we are interested in the coincidence limit of the Weidmann function, which is of course singular, and the standard way of subtracting the vacuum energy, if you will, of the ground state is to subtract the Minkowski space. But perhaps a more axiomatic way of doing it is to subtract the Hadamard by distribution of the relevant wave operator that defines the wave equation. So this is the modern way of renormalizing that we use in curved spacetimes. And since I'm coming from a curved spacetime tradition, I think this axiomatic approach is preferable and more generalizable if we wanted to go to curved spacetime. So we introduced this Hadamard by distribution, which is a solution, a parametrics to the Klein-Gordon operator of interest. And here I'm restricting to the case in which the potential term is vanishing. So this makes things simpler to study. Here, sigma is nothing but the half-squared geodesic distance. So it takes this particular form in Minkowski spacetime. Gamma here is just the Euler-Mascheroni number. And there are some ambiguities in the choice of this Hadamard subtraction piece. We have chosen it so that the Minkowski vacuum energy is 0. So this is appropriate for the Casimir effect. But when you don't make this choice, you have some ambiguities, which are usually renormalization ambiguities in more general contexts. So you can see that in 1+1 dimensions, so two space-time dimensions, we have a leading singularity, which is logarithmic. And this is, so when sigma goes to 0, this diverges logarithmically, and this is the term that we need to renormalize. So let's do it. So how do we define the bulk local Casimir energy or energy density? So we apply this operator to the two-point function, and we subtract the application of this operator to the Hadamard subtraction piece, or by distribution. So this is now regular in the coincidence limit, and we can take the limit when t prime and z prime go to t and z. So now this is going to give me the expectation value of the Hamiltonian, of the renormalized Hamiltonian. And notice that this operator that I'm using here, so if you would put a classical field and take the coincidence limit, this would just be the classical energy. So this is why this point splitting prescription is very natural. Now for the boundary local Casimir energy, here we have to understand a little bit more the meaning of these parameters. So as I said, this beta 1 prime looks like a propagation speed of the boundary observable, and the minus beta 1 looks like a mass term. So the natural energy associated to the boundary observable is by applying this operator 15a. And in this case, if everything goes correctly, we should have, under this renormalization prescription, a finite Casimir energy on the bulk, and the boundary should not require renormalization because this is just this is not field theory. You don't have space dimensions. The spatial component is just a point. So you wouldn't expect any divergences, and if everything goes correctly, this is what will happen. And I anticipate that this is what will happen. So let's study the case of a Dirichlet boundary condition at z equals 0 and a dynamical boundary condition at z equals L. Excuse me. I'm going to assume the potential term is 0, and I'm going to admit a non-negative mass. So in this case, I can write down the Weidmann function quite explicitly, because I can calculate these eigenfunctions in an explicit way. They take a complicated form, but they are just sines and cosines. So not too bad, even though the renormalization constant is a bit complicated. And what is a bit harder to find, as usual, is eigenvalues. So even though we have the eigenfunctions, we don't have the eigenvalues in closed form. And we need some large eigenvalue estimates to control the ultraviolet, which is tantamount to the short distance behavior of the Weidmann function. So our large eigenvalue estimates, we obtain them in their papers, take this form. So they grow like n, but then they get corrections that become suppressed at large n. And this estimate is enough for us to compute the Casimir energy. So we find for the bulk the following expression. So we have the first two terms in closed form, okay? So this is after renormalization. The first two terms, we have them in closed form. So note the presence of the first term has a logarithmic singularity when z goes to 0 and when z goes to L. So this behavior is nothing to be afraid of. It's standard. Also, if you put two Dirichlet boundary conditions, you know that you have these logarithmic singularities near the walls of the box, and this probably has to do with the modeling of the problem. But what is important is that these logarithmic singularities are integrable, so the total energy of the system is finite. Okay, and then we have some terms that are not so explicit that we have left out as sums. Okay, because we don't have the eigenvalues in closed form. We cannot give a closed form expression, but we can control these sums. We know that they converge absolutely and uniformly in Z in the interval. And we know how they behave at large n. They go like n to the minus 2, so they converge, of course. And you can see that the bulk local Casimir energy is conserved because it's time independent. And as I mentioned, this logarithmic divergence near the extrema of the interval are integrable. For the boundary, we have likewise an expression in terms of a sum. We know that it converges absolutely. And we know that at large n, it behaves like n to the minus 3. So the sum converges rapidly, or more rapidly. More rapidly than in the bulk case, not rapidly in the technical sense. And again, it's time independent, so this boundary energy is conserved. So we have a numerical example for some particular choice of parameters where you can see how these logarithmic singularities for the bulk Casimir energy look like. Okay, so you can see that. So this is for L equals 1. You can see that you have these logarithmic singularities. Okay, so these are using some approximation of some numerical approximation of the first 50 eigenvalues of the problem. Okay, we have other examples of the Casimir energy in our paper. Okay, so let me go now to finite temperature. You write the 2-point function for a field in a thermal state at temperature 1/β that is positive, and you can likewise compute the bulk and boundary Casimir energies. So you find that they differ to the ones in the vacuum by some complicated looking sum, but in fact these sums converge absolutely and exponentially fast in both cases. And moreover, for the bulk field, they converge uniformly in Z in the interval. So they converge very rapidly. Okay, so now let me go to coherent states, which is the case that we studied in the second part, if you will, second paper of the talk. And here we consider a unitary operator in Fock space, okay, phi f, where f is just a test function. So let's say of compact support, and we define we define a coherent state as the application of this unitary operator to the vacuum. Okay, we can compute the 2-point function in the coherent state using the Baker-Campbell-Hausdorff formula. So this is straightforward. And it takes this form where this phi f is now a classical solution of the problem. And it takes this form. So this is the f that we chose as a test function. So this phi f looks like applying the causal propagator to this test function. And this is, of course, a solution to the problem. The causal propagator of the system looks like this. Okay. And if you will, more explicitly, you can write these solutions by acting on the causal propagator of the test function. You get an explicit eigenfunction expansion of how these classical solutions look like. Okay, so now I've just said words and I've told you that this is a classical propagator, and now you don't believe me. So we have a proposition in one of our papers that shows that this is the causal propagator. So first of all, we show that these guys are solutions that are continuously differentiables in T and Z, and that the derivatives are uniformly bounded for T in the reals and Z in the interval. So we can actually compute, we have enough regularity to compute the Casimir energy. And now we prove that actually E is the integral, we can view it as the integral kernel of a causal propagator for the problem, and that it is unique in this theory. And this is important because this theorem implies, together with some classical results of causal propagators from the old age by Lichner-Ovix, this implies that the theory satisfies something called F-locality, which is an important property in axiomatic quantum field theory. It means that if I do physics, if I work with a field confined in a box, but I do physics far away from the walls in a causal diamond, I cannot see, morally speaking, I cannot see the difference. I cannot perceive the effects of the wall sufficiently far away. Okay, so now I can define the classical energy, the energy associated to these classical solutions just in the standard way. So, and I can do it for the bulk and the boundary contributions. And I find, we find in our papers that then, as expected, the energy in the coherent states is nothing but the energy of the vacuum plus the energy of the classical solutions, both for the bulk and the boundary. Okay. Then you can do likewise for some finite energy coherent states. So you put, so you do it similarly, but define the coherent states not with respect to the vacuum, but with respect to a thermal state, and you find again that you have corrections to the energy in a thermal state by the classical energy of the classical solution to which this coherent state is associated, and likewise for the boundary case. So let me just end with some remarks here. I've shown some examples in the case where you have a Dirichlet boundary condition at z equals 0, but you can do it also for Robin. It's done in our papers, and it's slightly more complicated. We also have in our papers expressions for the bulk and boundary state polarization, so that's the observable squared. And in our papers, we also study the Casimir force. Okay, so this is integrate the Casimir energy and then take a derivative with respect to the length interval and put a minus sign. So that defines the Casimir force. We studied it by a combination of analytic and numerical techniques. From a mathematical point of view, it's interesting that A is not the abstract wave operator is not a self-adjoint extension of some L2 symmetric elliptic operator on C naught infinity, which is what standard, let's say, standard theory, according to people like Wald or Ishibashi, would be to impose boundary conditions. But it is a self-adjoint extension of some operator in some extended space. So there's some mathematical interest here. The theory is F-local, which is interesting for axiomatic quantum field theory. And well, you could ask the question, if you do this in more dimension, it's probably difficult to obtain rigorous results, but perhaps not impossible. And it's also interesting to think of time-independent beta coefficients. This seems to be of experimental relevance. So for the dynamical Casimir effect, let me say. So I'll leave you there with it, and thank you. These are the papers that we have written if you're interested in having a look.
Many thanks, Benito. There are questions or comments? If someone has any question, please raise your hand. I have one.
Yes.
In the slide 17, how do you fix the parameters?
That's an interesting question. Oops, excuse me. So this plot was a first, let's say, exploration of the numerical of trying to obtain some numbers out of this abstract analysis. You see. So for this example, we just take beta 1 prime, beta 2, and beta 2 prime, so in such a way that our proposition holds, and make the easiest choice that you can make. So we can make -1, 1, 1, and 1/2. This is chosen so that the proposition holds, and then make the mass equals to 1 and L equals to 1. So you see, it's a very simple choice. But then we have other examples in our papers where we're actually saying, okay, how much this plot changes if I change the numerical values in this and this form. And those are more interesting, where we have actually, if you will, explored the parameter space to see what different features these plots could have. So this kind of behavior is generic, but the integrated energy could change. It could shift upwards or downwards, and also different choices of parameters also give you different behavior for the Casimir force. So in the couple of papers that we wrote on which I based this talk, there's a much more thorough, let's say, numerical exploration where we actually judicially choose these parameters in such a way that, let's see if we can get a negative Casimir force. Let's see if we can get a positive Casimir force to get a more thorough picture of this kind of system. But for this particular plot, we just went for the simplest possible choice that we could think of.
Thank you. More questions? No?
Okay.
No? Nobody? No. If not, thanks again, Benito.
Thank you very much.
and continue in 15 minutes with the tribute to Salvador. Now is time for a cup of coffee or something like that, and come back in 10 or 5 minutes. Thank you.